the day. I feel it falling, nothing comes to my mind. Bring it on in a different tide. I feel alright now. I feel strong, I feel rigid. It's nothing to do with the vision. Oh, feel so right, so right. Sleep on tight. Sleep on tight. Sleep until sunlight. Sleep until the sunlight. Sleep on tight. Sleep on tight. Sleep on tight.
Sobre el preguntarse cuál es su manera estática, cuál es la medida corporal encontrada que funcionalmente pueden llamar a un cuerpo estándar de medición. Lo que hace que sea muy simple es un principio que era, imagino desde años y años atrás, donde se toma un cuerpo y se sumerge en el agua, y cuando el cuerpo sumergido en el agua, los cuerpos con mismo volumen pero con diferentes densidades muestran diferente masa de agua, así que imaginen que peso 175 libras, ahora si tengo un gemelo que pesa 175 libras, pero él es realmente grande, pesamos lo mismo pero nos mostraremos diferentes de la masa de agua y que tendremos diferentes flotabilidades también porque las cosas de la grasa flotan un poco más por lo general. Así que si usted utiliza el principio para tratar de descubrir la fuente de densidad, entonces tenemos número y una cantidad de agua puesta que nos dirá qué tanto peso tendremos una vez sumergidos en ella, entonces podremos calcular qué porcentaje de grasa corporal tenemos.
Fuerza de flotabilidad. ¿Qué es fuerza de flotabilidad? Entendamos el sentido del término de punto de fuerza mediante el simple experimento de empuja el corcho hacia abajo en el agua opuesta a un canal. ¿Qué es lo que observas? Que el corcho salta y viene hasta la superficie tan pronto lo sueltes. Ahora manténlo en el fondo del agua, tendremos una fuerza descendente. Eso significa que el corcho está experimentando un punto de fuerza, una fuerza hacia arriba a la salida, es debido a la fuerza ejercida por el agua la cual ejerce hacia la superficie. Esto muestra que cuando un cuerpo es parcial o totalmente sumergido en el líquido ejerce una fuerza hacia arriba sobre el cuerpo. La fuerza hacia arriba experimentada por el cuerpo cuando parcial o completamente sumergido en el fluido es llamado empuje hacia arriba o fuerza de flotabilidad. El fenómeno responsable del empuje hacia arriba es llamado flotabilidad. Lo último a realizar es un sencillo experimento para probar esto. Suspende un objeto de una pesa de gancho, observa el peso, ahora sumerge lentamente el objeto entre el contenedor de agua. ¿Qué es lo que observas? Se observa que la pantalla de la balanza está indicando menos peso comparado con la primera lectura. Ahora saca lentamente el objeto del agua, vemos que la lectura de la balanza aumenta lentamente. Esto nos muestra que cualquier objeto parcial o totalmente sumergido en el agua o cualquier líquido experimenta la fuerza hacia arriba llamada fuerza de flotabilidad. Y esta fuerza es responsable de la aparente pérdida de peso del objeto sumergido.
This is the water density chart, and this is how you will find the density of the water to make your measurements accurate. We got a reading of 30 degrees Celsius in our tank today, so we'll look across and find that the density of the water is 0.9957.
That's interesting. 1 cubic centimeter of water has a mass of 1 gram. This is not a coincidence. If you research the history of the metric system, you will find that the first standard metric unit of mass, the gram, was defined as the mass of 1 cubic centimeter of water. The spectacle unfolding behind me here is a graphic demonstration of buoyant force. Amazingly, the buoyant force acting on a hot air balloon is able to lift a basket filled with passengers. This powerful force appears whenever an object is immersed in a fluid. Do you know what fluid this hot air balloon is immersed in? Remember that both liquids and gases are fluids. The fluid surrounding the balloon is air. Let's investigate the buoyant force in another fluid, water. This is a concrete block. This is a wood block, a softwood block, pine actually. I'm going to drop these two blocks into the water in the aquarium. One will sink, one will float. You probably have a prediction about what's going to happen. Let's find out. I suspect your prediction was correct, that the concrete block sinks. When I ask the question, why does the concrete block sink? The answer often is the concrete block is heavier than the wood block. We have to be careful with our vocabulary and understanding here. Consider a cruise ship. More buoyant force. This cruise ship behind me is in fact a huge hotel floating on the surface of the ocean. These huge ships can weigh over 50,000 tons. Despite this huge weight, cruise ships have no problem floating on the ocean. Whether an object sinks or floats is not determined by its weight, but by its density and the density of the fluid it is immersed in. Density is mass per unit volume. Back to our investigation of density and buoyant force, this table shows the wood is less dense than water and that the concrete is more dense than water. The wood block floated while the concrete sunk. A conclusion from this data is that objects denser than water will sink in water, while objects less dense than water will float on water. This is true for other fluids, not just water. This means that the cruise ship, even though it is extremely heavy, is less dense than salt water. This is because a large portion of the volume of the cruise ship is air. Sometimes an object neither sinks nor floats. We say it has neutral buoyancy. Fish can adjust their density to maintain a state of neutral buoyancy. They do this by inflating an internal bladder with air. This organ changes the volume of the fish without changing its mass, allowing it to match its density to the water it is swimming in. Scuba divers use a similar method with an external bladder to control their buoyancy. Human beings are very close to having a neutral buoyancy. The makeup of each individual determines whether they sink or float. We have demonstrated that density determines whether an object will sink or float, but we have not explained where the buoyant force comes from. When an object is placed in a fluid, it displaces or pushes out of the way some of the fluid. This displaced fluid pushes back on the object. This is buoyant force. All objects in a fluid experience buoyant force. Even the concrete block on the bottom of the aquarium is experiencing a buoyant force, but the force is not strong enough to lift the block. The Greek philosopher and scientist Archimedes is credited with figuring this out. The science behind buoyant force is known as Archimedes' principle. This principle states, the buoyant force on a submerged object is equal to the weight of the fluid that is displaced by the object. This means that the denser a floating object is, the more water it will displace. An object with a density of 0.5 grams per cubic centimeter will float only partly submerged, while an object with a density of 0.9 grams per cubic centimeter will float almost completely submerged. Another interesting thing about buoyant force is that gravity plays a role. You may know that pressure in water increases as you dive deeper in a lake. Gravity creates this pressure gradient, and it is an essential part of buoyant force. It is not possible to create a buoyant force without gravity.
Space-time. And so if I have another object that also warps space-time, they feel that and they're attracted to each other. And so that's Einstein's picture of gravity. Objects warp space-time, feel that curvature, and move accordingly. And if you have more mass, it's going to bend space-time more. And so if you have objects here, they are going to respond to that, right? And so you put something there, now it's attracted. Now, in reality, that big mass would feel the warping of space-time by the marble too, right? It would move a little bit, but we usually ignore that. You know, the Earth makes the sun move a little bit, but it's so small you can ignore it. The moon makes the Earth kind of wobble around a point 3/4 of the way from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse. Wow. Direction. But there was a preferred direction, which just informed from it